So we're going to look at the relationship between vapor pressure and temperature. It's not linear, as we saw in that previous graph. It's actually exponential. And it can be described by this equation, which is kind of messy. But we can rearrange this and make it into a linear equation. This is called the Clausius-Clapeyron equation. The natural log of the vapor pressure is equal to the heat of vaporization, negative heat of vaporization divided by R, times the quantity 1 over T, plus a constant, the natural log of this constant beta. We're not really going to care about that at all, but we do care about this. This is in the form of a line equation. So remember, the equation for a line is y equals mx plus b. So this is y. 1 over t is x. And then negative heat of vaporization divided by r is the slope of the line. Any questions? You look stunned. Everybody's
So
like,
this is
what?
The y, that's the m, and that's the x.
So the y is the natural log of the vapor pressure. So that's what we graph on the y-axis. And we graph 1 over t, and the t there needs to be in kelvins, because you don't want to have 1 over 0. That gives us a big problem. So we use Kelvin temperatures. 1 over Kelvin temperature on the x-axis, and then the slope of that line that results will be equal to negative delta H vap over R. So this is what that sort of a plot might look like. The natural log of P, the vapor pressure over here, against the 1 over the temperature in kelvins. So you see now, instead of a curve, we have a straight line. It's not perfect, but it is definitely a straight line. So you can use linear regression and find the equation for the line. Here we've determined that the slope is negative 3478 Kelvin. And so that's equal to negative delta H over R. And if we know what R is, then we can solve and find out that the delta H is 28.92. And the times 10 to the third joules per mole. Any questions about that? We're going to use the form of the gas constant that has joules per mole Kelvin as the unit. So it's the 8.314 instead of the one we used for the gas laws. So let's do an example here. The vapor pressure of carbon tetrachloride is measured as a function of the temperature, and the results are tabulated. Determine the heat of vaporization of carbon tetrachloride. So this is not the sort of a question that might show up on an exam, because it requires you to make a graph and do linear regression, and that's a little hard to do on an exam. But this could be a homework problem, and I want to take you through it so that you see what's going on here. Now we'll see what happens if I can get this to work with the recording. I think it's going to be okay. So what I've done here is I've opened an Excel spreadsheet and I put the data in here. Okay, so I've got temperature in Kelvin and pressure in torr. But we want to graph the natural log of the pressure and 1 over the temperature. So I'm going to use the spreadsheet to do that for me. So 1 over T, that's going to be equal to cell A, 1 divided by cell A2. So that's 1 over the temperature. And then we'll just fill that in for those other boxes, and then we've got all of our temperatures. Isn't that easier than doing it on a calculator? And here we have the natural log of P, and so that equals ln of B2. There's the natural log of...
Is this going to come out on your YouTube video?
Yeah, this is all being recorded on the video. Yesterday I didn't have it together to do that, but today it seems to be working. So there's the natural log of P. So we want to make a graph, so we go up here and we go insert chart. I want a scatter plot. And so what is it graphing here? It's doing funky stuff like it often does. Yeah. So I'm going to select the data, and this is the data I want. gonna let me do it. What? Okay. D. Fine. This is what happens when you try to do things. Oh, fine. Yes. Chart. There we go. And I'm sorry, I cannot really tell you how I did that because I just click buttons and sometimes it works and sometimes it doesn't. Normally we'd want to put a title on this and label the axes, but we're not going to worry about that right now. I can tell that I have my x and y points correct because on the y, this is going, between 0 and something around 6. Right, and that's what these values are. Well, this one's negative, that's okay. And then these values are really small. Sometimes you'll get your x and your y backwards, and then that makes a mess. So then if I go on this, on the line, one of these points here, I can go add trend line, display equation on chart, display r squared just for fun, and get rid of this. And so there's my equation for the line. Okay. And the slope is what we want here, that negative 3773.5. We don't care about the intercept. Now, yesterday, as I was doing this, I had this scary thought, what about the units on the pressure? Because a lot of times that matters. And so I did it in torr and I did it in atmospheres. And the only thing that changes is the intercept, which we're not caring about anyway. The slope comes out exactly the same. So that's not a problem. But this is the number we need, minus 3773.5. So we'll go over here, see if I can get this to work again. And we graph the data, and we find that the slope equals minus 3773.5. The unit on that is going to be Kelvin. If you want to know why that is, I could show you that later. So the slope is equal to negative delta H Vap over R. And so that is equal to that numerical value that we just found. Any questions so far?
Is there going to be homework that we need to use graph?
There could be a homework where you'd have to do this. I don't remember what I assigned off the top of my head. Get rid of that. Fine. We'll just live with that box up there. So then what we need to do is we need to put in our value for R and solve this equation. I'm going to start out by just getting rid of those negative signs. If I multiply both sides by -1, then I get this, right? So the negative signs went bye-bye. We're going to use an R value, the 8.314 joules per mole Kelvin. And so when we rearrange this, we're going to multiply both sides by R. So delta H vaporization equals R times that 3773.5 Kelvin, which equals 8.314 joules per mole Kelvin times 3773.5 Kelvin. Oh, where's my calculator? .314 times 3773.5. So the heat of vaporization equals 31372.879 is what my calculator is giving me. And the units on that, the kelvins cancel, And so the units are joules per mole. So what do we do with sig figs there? Well, when you're dealing with graphing an equation and graphing data and getting an equation, then you can't really use significant figure rules. There are other ways that you could determine that, but we don't need to mess around with that. So we're just going to try to get close. Let's look at the data, right? This appears to be to the nearest 10 Kelvin, but hopefully they would have measured it a little more accurately there. And this is, most of these have 2 or 3 sig figs. So let's just kind of say, well, 3 significant figures would be reasonable and really not worry about it beyond that. So if I keep 3 sig figs, and then I look at this is a big number, and it's joules per mole. It'd probably be better to make it kilojoules per mole, right? So kilojoules would move the decimal point 1 to 3 places. And so a nice answer would be 31.4 kilojoules per mole. Any questions? Yes?
Where did you get the negative 377?
This came from the graph that we made. So it took this data and graphed natural log of P versus 1 over K, 1 over T in Kelvin, and this was the slope of the line.
What part of the slope is the one you're talking about exactly?
Well, let's see. Come on. This is the line that we got, and so there's just one slope. By using that Clausius-Clapeyron equation, it takes it from an exponential curve to a linear function.
So is it just any one of those dots, or you just put the mouse on there and it'll say the number?
No, so I put the mouse on here and I told it to do a trend line, and so it does linear regression, and it gives me this equation, y equals negative 3773.5 x plus 18.692. This is the intercept that we don't care about, and that's the slope of the line. Any other questions? So you can also take this equation and make it into a 2-point form, so you don't actually have to graph the data. Okay?
I don't like graphing.
Well, the 2 different forms are useful for different situations. The one we just looked at is useful if you're trying to figure out the heat of vaporization. You can measure the vapor pressure at different temperatures and do the graph and find that. If you know the heat of vaporization and you're wondering what the vapor pressure will be at a particular temperature, then you can use this equation to find that. So here we have the natural log of P2 over P1 is equal to the negative delta H vap over R, that was that slope we had before, times the quantity 1 over T2 minus 1 over T1. Again, those temperatures have to be in kelvins. The units on the pressure just need to be the same, P1 and P2.
The T2 and T1, is that final temp minus initial temp, or is it just two different temperatures?
It's just 2 different temperatures. It's the temperatures at which you know or want to know the pressures.
Oh, okay.
To find the vapor pressure, how would we do that?
How would you do that?
Using this equation?
Well, I'm going to show you. So this is the sort of problem, and this could be on an exam like this. I'll give you those equations, but you need to know how to use them. So propane has a normal boiling point of minus 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure of propane at 25 degrees Celsius? So this is a situation to use the 2-point form of the Clausius-Clapeyron equation. So let's write that down. The natural log of P2 delta 2. There we go. Over P1 is equal to negative delta H vap over R times the quantity 1 over T2 minus 1 over T1. So we're looking for a vapor pressure. So we need a pressure, and we need two temperatures, and then we can solve for the other pressure. And you can choose which is 1 and which is 2. Are we going to solve for P2 or are we going to solve for P1? I like to solve for P2 because it's a lot easier. So I'm going to say that this vapor pressure I'm trying to find is P2. So vapor pressure, P2 is what I'm looking for at 25 degrees Celsius. So that means that that's T2. I'm just deciding it's T2. I could do it T1. You can still come up with the same answer. I just think it's more difficult to solve the equation that way. So we're going to add 273.15 to get this into Kelvin. We get 298.15 Kelvin. Now, we've got the heat of vaporization right there. That's cool. And it says normal boiling point of minus 42. So we have another temperature. So that's going to be temperature 1. And we have to convert that to Kelvin also. So 273.15 plus negative 42 is 231.15 Kelvin. But what is the vapor pressure at that temperature? What does normal boiling point mean? At STP, at atmospheric pressure, normal atmospheric pressure. So the normal boiling point is at 1 atmosphere of pressure. It's hiding in there, right? So P1 equals 1 atmosphere. Exactly. Because that's how the normal boiling point is defined. Now you could do it in Kelvin, in torr or millimeters of mercury or some other pressure unit. But the question doesn't specify a unit, and so if it lets me choose, I'm going to choose something easy, and we'll find out that doing 1 atmosphere is very easy here. Okay, so now we've got all of our things. This is a situation where it is best to just put the numbers in and then figure it out, because we're going to have pressure 2 that we're looking for over here by itself, and then all of that will become a number, and so we'll deal with that. So plugging the values in, the natural log of P2 is what we're trying to find, divided by 1 atmosphere. So that makes that term really easy. Equals negative heat of vaporization, 19.04 kilojoules per mole, over R, 8.314 joules per mole Kelvin, times the quantity 1 over, we need T2 first, it's 298.15 Kelvin, minus 231.15 Kelvin. So now we can do some calculating here. Because P1 is 1, P2 divided by 1 atmosphere is just P2. So the natural log of P2 equals, and then we have to talk to our calculators carefully. Look at the units. Is there a problem with those units? We've got kilojoules up here and joules down here. So we would like to get those the same. Yeah. Yes, that's R. I would give it to you. There's different expressions of the ideal gas constant depending on what units you use. So 0.08206 liter atmospheres per mole Kelvin, but liter atmospheres are related to joules, and so then it's 8.314 joules per mole Kelvin. And you can do it in other units also.
Yeah, because a few times I've forgotten it and Googled it.
Yeah.
It comes up with this huge long list.
Right. It's like, you know, whatever one you want. Yeah. But it's the same quantity. It's just like, you know, if you measured something and it's 10 inches or it's 25.4 centimeters, it's the same length, just different names for the same quantity. That's all it is. Okay, so I like to just convert by, instead of having kilo in there, writing what kilo means. Kilo means 10 to the third, so times 10 to the third. So then my calculator, I'm going to go negative 19.04 EE3 divided by 8.314 times, I'm going to use parentheses, 1 divided by 298.15 minus 1 divided by 231.15, close the parentheses, enter. Depending on what kind of a calculator you have, you may need to do that a little differently. So I end up with this long thing. And if you look at the units now, all the units are going to cancel out, which is what we actually expect to happen because the natural log of a ratio that has no units is going to give us a value that has no units. So to solve this for P2, we need to do the anti-natural log, which is e to the x. So P2 is going to equal e to that big old long number. Blah, blah, blah. Can't make periods. Okay, so I'm going to go e to the x, and then I'm just going to pull down that value so I don't have to enter it again. And so this is equal to 9.2664 and a bunch of other digits. What unit should that pressure have? ATM. Because in this ratio, we plugged in P1 in atmospheres. If we use torr here, then we'd need to do torr. So the unit here is atmospheres. In terms of significant figures, again, let's just try to be reasonable. I'd say the most you should have would be 4 based on this. So we could say, well, we think it's 9.266 atmospheres. And then ask yourself, does it make sense? So propane boils at minus 42 degrees Celsius. That's where its vapor pressure is 1 atmosphere. When you heat something up, does the vapor pressure get greater or smaller? Greater. So we're expecting P2 to be greater than 1 atmosphere. 25 degrees is a significant temperature increase. And so, 9.266 atmospheres is a high pressure, but it's not unreasonable. Any questions? Yes?
The R is automatically equal 8.314.
Yeah, it's a constant. So there's 2 different values that we use, 8.314 joules per mole Kelvin and 0.08206 liter atmospheres per mole Kelvin.
So are we just using the 8.3 for this section?
Right, because here for delta H, we've got joules. We're talking about energy here. And so if we could use the liter atmospheres one, but then we'd have to introduce the conversion factor and convert joules to liter atmospheres or vice versa, and that would be annoying. Any other questions? So what if you take a liquid and you vaporize it, you heat it up in a sealed container. And you just keep heating and keep heating. As the temperature rises, the vapor pressure rises. And as the vapor pressure continues to increase, the gas becomes more dense. And eventually what happens, the gas becomes more dense, the liquid becomes less dense, and at a specific temperature called the critical temperature, the two states actually merge into one. And so this is looking into a special chamber. Here you've got a gas and a liquid. You heat it up, and the gas becomes more and more dense, the liquid becomes less dense, and once you get to the critical temperature and above, the phase becomes one phase. There's no division between, but it's not a gas.
So it's not a gas, but it's not a liquid?
It's not a gas, it's not a liquid. It's a supercritical liquid.
That's just what it's classified as?
Yeah, supercritical fluid.
So technically there's 4 states in there?
Well, actually there's plasma.
So there's 5?
Well, we don't usually think of a supercritical fluid as a state of matter. So you could argue that, and we're not going to right now. But we could do that later if you like.
So what properties does a supercritical fluid have?
It has very, very interesting properties.
Is it like halfway between liquid and gas?
Yeah, I mean, it's more dense than a gas, less dense than a liquid, but it's a fluid. Now, if you let it cool down, or you open the container, then it's going to revert to either gas or liquid or both. But it's really useful for certain things. So what we call the critical temperature is the temperature above or at which the supercritical fluid forms. And above that temperature, you cannot have the liquid.
You can't put the gas in.
Well, you can have the gas at a low enough pressure. And so the pressure that you observe at that temperature is called the supercritical pressure. Supercritical fluids are awesome solvents. In fact, supercritical carbon dioxide is used to decaffeinate coffee. So decaffeinating coffee, you want to get the caffeine out of the coffee beans without taking out the stuff that makes the coffee taste good to some people. Pardon me?
Which they do anyways.
Yeah.
There's no decaf coffee.
Well,
It tastes as good as regular coffee.
I detest coffee, so I know, it's terrible. Swedes are supposed to love coffee, and I can't stand this stuff. Anyway, so you want to get rid of the caffeine and remove as little as possible of the compounds that make the coffee taste good. We'll qualify that. And you also don't want to leave behind harmful residues. So you can use a supercritical CO2 fluid, and that will extract the caffeine out, and it will not take out most of the other things. Okay? And then you flush that fluid off, and any that's left, when you let it out of the chamber, it just turns into a gas and leaves nothing behind.
Does the whole process have something to do with why decaffeinated beans are not shiny and caffeinated beans are shiny? Have you noticed the difference?
It's the oils, right?
Well, I
Is that
don't
what it
look
is?
at them.
You don't?
It certainly could have something to do with that. Yeah.
I think what it is that it's when you decaffeinate the coffee, it pulls some of the oils off of it. A lot of
It might pull some of the oils off.
decaffeinated beans are like flat,
Matte finish.
like a kind of a matte finish, and
Yeah.
caffeinated ones are all.
I hadn't actually noticed that. My husband rarely drinks decaf. I can make really good coffee. I've been making coffee for like 27 years, but I don't drink this stuff. This is an example of a common problem that chemistry addresses. We need to separate out one or two components from this mixture of stuff. So we have this natural coffee bean, and we want to take something out of it. And we use chemistry to figure out how best to remove the thing we want to remove and leave the other stuff behind. This happens in all sorts of situations. Very simple example is you cook spaghetti at home, right? And you boil the water, you put the spaghetti in there, you cook the spaghetti. Now you need to separate the two, right? Well, that one's pretty easy because the spaghetti's solid and the water's liquid, and so you just use a colander and separate them that way. But there's a whole branch of science, separation science. Any questions?